going to talk about logical pre- and post-selection paradoxes.
Thanks, Matty. So this is the title of the paper that I've written with the other Matt. But for the purposes of this talk, the title's going to be a little bit simpler. It's that the three-box paradox is a proof of contextuality. The connection is that the three-box paradox is an example of these logical pre- and post-selection paradoxes. And it's just a bit easier to explain the basic ideas with a specific example in mind. So what is the three-box paradox? So it's a quantum experiment that you can do in a three-dimensional Hilbert space. So you just choose some bases for that Hilbert space, 1, 2, and 3. And just to kind of make things sound a bit more exciting, we're going to call this a ball being in box 1, this is a ball in box 2, and this is a ball in box 3. Okay? So you start by preparing an equal superposition of those three states. And then the last thing you do is you do a measurement that includes this outcome. So it's another superposition but with a different phase here. And we're only going to be interested in runs of the experiment where that final measurement gives us this outcome. Okay? So that's called post-selecting on this state. And the reason I've told you the first step and the last step before I've told you what comes in between is that these are just kind of thought of as boundary conditions for the experiment. Okay? So this is how the system starts off, and we're only interested in cases where the system ends up being measured in this state. So we kind of, these are just background assumptions for all the stuff that goes on in between. So what does go on in between? Well, there's two things you can do. You can look in box 1, which just means doing a projective measurement either onto 1 or onto the rest of the Hilbert space. Or you can look in box 2, which is projecting onto 2, so that's the ball is in box 2, or the ball is not in box 2, the rest of the Hilbert space. And it's not too hard to work out what's going to happen here. So let's suppose that we did this first measurement, we looked in box 1, and suppose that we got this outcome. Okay? Well, so we're just doing a normal projective measurement with the Lucas update rules, so the state just gets projected by this operator. Okay, so we're just going to project into the 2-3 subspace. So that means we're going to end up with a state that's proportional to this. But we can see that this is orthogonal to this final state that we're post-selecting. So if we get this outcome of the intermediate measurement, we know that the post-selection is going to fail, and so we're not going to count that run of the experiment. So in the runs that do count, it must be we get this first outcome. Similarly, if we look in box 2, if we were to get the outcome that it's not in box 2, we would project onto the 1 and 3 part of this state. That's again orthogonal to the post-selection. And so whenever we got that outcome, the post-selection would have failed. So given that the post-selection has succeeded, we must get this outcome. Okay? And then the paradox is supposed to be that under these assumptions, if we look in box 1, we always see the ball there, and if we look in box 2, we also always see the ball. Okay? And it kind of strikes you immediately that there's a sort of whiff of contextuality about this, okay? Because it sounds like the answer we're getting depends on the question we're asking, right? If we're asking, is the ball in box 1, we find that the ball is in box 1, whereas if we ask, is the ball in box 2, we get the answer that it's in box 2, okay? So we're getting different answers depending on which question we answer. So you might naively think that this is a proof of the Cauchy-Spector theorem. Okay. So what's the Cauchy-Spector theorem? That's the incompatibility of quantum mechanics with a certain type of non-contextual model. So this whole discussion is just going to be based on the kind of standard realist framework for talking about no-go theorems, the same sort of things that go into Bell's theorem. So I'm assuming there is some real description of the system, and I'm going to add certain assumptions about what that real state is. And the assumptions you add in for the Cauchy-Specker theorem are that the real state determines the outcomes of projective measurements. Okay? So if you know the real state, then you know the outcome of a projective measurement with certainty. And the other assumption, the non-contextuality assumption, is that whether or not a projector happens is independent of the other projectors in the measurement. Okay, so another way to put it is that the real state of the system is just a function from projectors to 0, 1, and when you perform a projective measurement, it has to be that exactly one of those projectors is given value 1, and that's the outcome that happens in the measurement. So, you know, this is starting to look even more suspect because it seems like, well, this outcome always happens, so shouldn't that get value 1? But this outcome also always happens, so shouldn't that get value 1? But then since we can also do a measurement that includes both of these projectors, it sounds like we've got a problem. In fact, we don't have a problem. This isn't a proof of Cauchy-Specker contextuality. And the reason is that this kind of very naive argument I just gave, where I said, well, this always happens, doesn't it get value 1? And, well, this always happens, so doesn't that also always get value 1? That has a bit of a loophole. Okay? So, a pedantic person who really wants to save ontological models, because they're an anti-quantum zealot, might write a paper with Rob Speckens pointing out that this argument doesn't really go through. So they gave a model that helps show this. I'll give one that's actually a little bit simpler. So here's our 3 boxes, and then I'm going to look in this box, and I see the ball. Okay? So these boxes were prepared somehow. Now I've taken the action of looking in this box, I see the ball, and now I hand things over to the person responsible for the post-selection, and they take a look and they say, all right, I'll allow that run. Okay? So this one passes the post-selection. Next, I decide to look in the next run of the experiment, I decide to look in the first box again. This time I don't see the ball. Then I hand things over to the post-selector, and he says, actually I've decided that the post-selection's failed, so you don't get to count that one. Okay, I look in this one, I see it, the post-selection succeeds. I look in this one, I don't see it, and sure enough, the post-selection fails. So now, given that we're only allowed to count the runs of the experiment where the post-selection has succeeded, we find the ball in whichever box we look in. Okay, but you know, it doesn't take a genius to work out what the post-selector was doing here. He was just looking at which box was open. If there was a ball there, then the post-selection was passing, and if there wasn't a ball there, the post-selection was failing. Okay. So in slightly more technical language, what we could say is that our act of measurement, i.e. opening a box, has disturbed the system, in this case because we've carelessly left the lid open after the measurement. That disturbance means that the system has information about which measurement was performed, and the post-selection can use that information to simulate the paradox without ever having to have a ball in more than one box. Okay? So if we're going to say that the 3-box paradox is a proof of contextuality, we need to explain why this is not what's going on in the quantum version of the experiment. Okay? And you might be already thinking that what I'm doing here doesn't really look like the intermediate measurements in the quantum case. You know, I'm opening this box and then I'm leaving it open. You know, surely an experimentalist wouldn't be that careless. we need some way of identifying, well, what does quantum mechanics tell us about how much disturbance there is in this intermediate measurement? Okay, but actually, this Cauchy-Specker notion of contextuality that I'm working with at the moment is basically just silent on that subject. Okay, it's all about what happens when you do a projective measurement. It tells you have to get this deterministic outcome, and it has to be context independent. But it really just says nothing about what happens to the state after the measurement. Okay, so as far as the Cauchy-Specker definition is concerned, this is a perfectly legitimate non-contextual model of the experiment. Okay, the only requirement that Cauchy-Specker non-contextuality puts on me is that I can't just put a ball in more than one box. And if you want a kind of more elaborate model that really reproduces all of the statistics of the quantum version of the experiment, there's a nice paper by Owen Morini that you can see. Okay, so I started by saying it has a whiff of contextuality. Then I said actually it's not a proof of the Cauchy-Specker theorem. The waters were muddied even further by this paper, which showed that, although admittedly they're not a proof of the Cauchy-Specker theorem in and of themselves, you can play with the sort of things you've got in your toolbox and rearrange things into a proof of the Cauchy-Specker theorem. Okay, so you don't do the three-box paradoxes I described, but you use the same measurements, and you basically change some things from being post-selections to just being normal measurements. And so a sort of simple way of putting it is that the structure in Hilbert space that's being used in the three-box paradox is actually sufficient to prove the Cauchy-Specker theorem. So it's not a proof of the Cauchy-Specker theorem, but it's closely related. So this is all a little bit unsatisfying. We just want a straight answer, is this a proof of contextuality or not? And the best way to get that is to use a more complete definition of what a non-contextual model is. And so that's the generalization of the Cauchy-Specker notion of non-contextuality due to Rob Steckens in this paper. And the idea here is we're going to sort of ask, well, what operationally is motivating this non-contextuality assumption that the same projector gets the same value regardless of which measurement it's in. And Rob argues that the fact that motivates this is that that projector gets the same probabilities regardless of which measurement it's performed in. Okay? And so the idea is just to elevate that to a general principle and say whenever two different procedures get you the same probabilities at the operational level, you should impose that they're the same in your underlying explanation. And so that principle in particular gets you the non-contextuality assumption of Cauchy-Specker, but it can also be applied to other things. So this word procedure can include preparations and transformations as well as measurements. And so the first thing you need to know about this notion of non-contextuality is that, as I said, it gives you the non-contextuality assumption of the Cauchy-Specker theorem. And if you throw in a few basic facts about quantum theory, you can also derive the determinism assumption of the Cauchy-Specker theorem. And so everything I said before about the Cauchy-Specker theorem still holds. So a Cauchy-Specker, a non-contextual model of three-box paradox still has to have the fact that there's a deterministic fact of the matter about which ball the box is in. But now there's going to be extra requirements because we've extended the principle of non-contextuality to preparations and transformations as well. So one thing we noticed about the disturbance in that model I gave you is that every time we did a measurement, we disturbed the system. Okay? Every time we opened the lid, we left the lid open, and so the system was left in a different state than it was before we did the measurement. And actually, if we're going to use anything like this to try and explain the three-box paradox, that's going to have to be the case. Because the ball either has to be in the first box and the second box. So let's suppose it's in the first. Well then if we look in the second box, we're not going to see it. And now we need that the post-selection fails. Okay? But Okay, one important thing I didn't mention right at the start, I'm not going to go all the way back, is that the state we prepare the system in and the state we post-select them in are not orthogonal. Okay? So if we didn't do anything in between, then certainly the post-selection would succeed some of the time. Okay? So if we have one of those states where the post-selection was going to succeed, the ball was in box 1, we look in box 2, we don't see it. The only way to prevent the post-selection from succeeding is to disturb the state of the system. Similarly, if the ball is in box 2, then looking in box 1 is going to have to disturb the state of the system. So any kind of model that tries to explain the three-box paradox in this way is going to have to disturb some of the states of the system are going to have to be disturbed every time you do a measurement. And that turns out to be a problem for the following reason. So let's suppose we're doing a two-outcome projective measurement of a system. If we get the first outcome, we update the state to this. If we get the second outcome, we update the state to this. And so if we just forget for a minute which outcome we got, then the new state of the system is just given by this. Okay? This is just the normal update rule for a projective measurement. And then we can just do a few sort of trivial rearrangements, just doubled the number of terms. I've thrown in something and subtracted it back out again, grouped things around a bit. Notice that, okay, so this was a two-outcome projective measurement, so the two projectors add up to the identity. And the upshot is that the transformation effected by doing a two-outcome projective measurement is actually equal, according to quantum theory, to the transformation of, with probability half, doing nothing to the system, and with probability half, doing some unitary to the system, which is given by this. Okay? So, for any, no matter what state we prepare, if we do the projective measurement and forget the outcome, the effect on the state is the same as if with probability half we've done nothing, and probability half we've done this measurement. And so this gives us a handle to apply this assumption of transformation and contextuality. Because
projections.
Pardon?
It's only when PQ are projections.
Yes. And it also matters that we're using the normal Luder's update rule. So transformation non-contextuality says that since at the operational level this transformation looks the same as this transformation, at the ontological level they have to be the same as well. But I've just argued that if we're going to dissolve the three-box paradox, then this transformation, i.e. doing the measurement, has to disturb some states of the system every single time. But this transformation, half the time, involves doing nothing. Okay? So at least half the time, the state of the system has to be unaffected. But transformation non-contextuality says that this has to be the same as this, even in the ontological model. And so we're just not allowed in this transformation to disturb the state every time. Okay? So this explanation of the three-box paradox that I gave you, although it's not contextual in a Cauchy-Specker sense, it is contextual in the generalized sense because it fails this application of transformation and contextuality. So now that I've given you the basic idea, why should you read the paper? Well, I explained it for the three-box paradox. That's just one example of something that has been called a logical pre- and post-selection paradox. It's called logical because those intermediate measurements happened with 0 or 1 probabilities. Pre- and post-selection, hopefully that's clear by now. And so there are many other examples of this. For example, if you've heard of the quantum pigeonhole principle, this is also a logical pre- and post-selection paradox. Okay, and we can basically run a very similar argument for any of these logical pre- and post-selection paradoxes. Another thing we do slightly differently is instead of using transformation non-contextuality, we can actually just use measurement non-contextuality. The idea is that doesn't really matter whether or not the intermediate measurement disturbs the system. What matters is whether or not it disturbs the post-selection. Okay, so we can just kind of focus our attention on that, and that means we only need to use measurement non-contextuality as applied to that final measurement. And that, for example, if you were going to sort of do a contextuality experiment based on this idea, that would just make your life a bit easier because it would cut down on the number of things that you need to check. So it's just kind of trying to minimise the assumptions a bit. We also discussed a bit about what would happen if you did weak measurements in between rather than strong measurements. And we give some examples showing that it really is important to the proof that these intermediate probabilities are logical, that they're 0 or 1, and that it's important we have this von Neumann-Luders updated. Thank you very much.